So I've started the recording. Just having a little, let me just get this thing up. This one. What's happening with this? Let's get this up. This. All right. Share. All right. So we'll now start our study. All right, so the outline is as follows for this lesson. We will start with application, then we look at the power semiconductor switches, then we look at the gate-based drivers, we look at losses, and we're going to then look at snowbird circuit, in particular the design. All right, so our power electronic system has two main types of application, the static application.
Sir,
and
have you started the recording again?
Yes, it has started.
Okay.
If you look, there are red light, little red button that you are seeing. Are you seeing it?
No, but that's fine, sir.
All right, let me just make sure it is being recorded here.
Yes, sir, it's being recorded.
Yes, it is being, all right, good. All right, so we have two types of application, the static and the drive application. Static, as the name suggests, it's not, there's no movement, right? So we don't have any rotation involved, right? No mechanical components that is moving, right? So I'll give you an example of that, like your power supply, UPS, right, and your HVDC systems, right? Heating, cooling, the electronic ballast. These are all static application. Yes, inside your electronic ballast, you'll find power electronics, right? So that's a static application,
Sir,
right? Yeah.
Are you sharing your screen?
Yes.
I am not seeing it. I see a black screen. I don't know if anyone else is seeing that.
Yeah, man, we're seeing it.
Oh.
You're seeing my screen?
Yes.
Okay. Oh, I'm not sure what is happening with your screen. Conrad, you seeing it? Huh?
Yes.
Okay, good. All right. So for the drive applications, right? These are now dealing with moving or rotating components like your motors. So when you look at electric vehicles, yes, you'll find power electronics there, air conditioning system, as we mentioned earlier on, pumps, compressors, conveyor belts. You'll find power electronics there. Right, so I'll give you an example of each type in a block diagram. right? So the first, you look at the static application, and here it's in relation to a DC power supply. And then we look at the drive application, and that's for your AC system, right? So looking at the first, our DC power supply, as you can see here, it takes in your AC voltage, then you have your diodes and your filters here, and then you have the power electronics at this part that will be converting this electrical power and convert it back to your desired output and level, right, by means of feedback, right, feedback control. All right, now when we look at the next application, right, so the drive application is using the AC system. All right, so the whole aim of this type of system is for you to have cooling. So how are you going to maintain a particular temperature? Also desired humidity, because AC units are supposed to not only maintain temperature but also humidity, right? So you would set your desired level for your temperature and your humidity, and then what is going to happen? Your power electronics, right, is now going to respond to these settings, right? So your motor and your AC unit will speed up, right, trying to get the building cool in a shorter time as possible, right? So it is constantly checking the temperature and the humidity using sensors, right? So if they're not what they're supposed to be with the introduction of the feedback loop, right, then the power electronics converter will then respond accordingly and forcing the output to be at the desired level of temperature and humidity. All right, so if we look at this, very basic, just to bring about the whole concept of conversion. So we have our diode here, which is basically a device that allows for one-way flow. So your AC comes in, and what you get out, only the positive cycles that you get out. There's the concept of average output voltage, right? We'll be looking at that. Or average output voltage in this case would be the peak divided by pi. So this peak voltage divided by pi would be the average output voltage. So that's how you do that type of calculation. If you're to look at another type of device that we'll be studying, it could be the silicon control rectifier, right? That's just the SCR, right? This type, unlike the diode, if you'll notice, the output voltage is fixed, right? Just the average output is fixed. However, with the use of silicon control rectifier, as you can see, the output, we're able to control different points at which we can turn this device on, right? So looking right here, we have the device turning on at a particular time, as opposed to when we use a diode where it comes on at a fixed point in the cycle, right? So how do we achieve this with this device? We just apply a narrow positive pulse to the gate of this device, right? So by applying this narrow positive pulse, you're able to change what we call our firing angle, right? And of course, we determine the average output voltage, right? I will get into this part in a little while, but before I do that, let me go back to these slides. I want to prove just a bit of proof here. All right, so in the case of just your diode, right, what you have, that's your input, and as it passes through your diode, let's say this is Vm, all right. Now we're now going to calculate the average output. When we talk about average, what do we mean? Average, we want to take the sum of all the points and divide by the number of points, right? So that's what average is about. Now we can use calculus in this case. How do we take the sum? Normally we use the integral, right? So we're going to take the integral right. So but what's the waveform we have here? It's a sinusoidal waveform, right? So this is sine omega t, and we're going to integrate with respect to omega t. Now so this is the sum. Where are we going to sum between? All right, so here is 0, here is pi, oh here 2 pi. Right, so between pi and 2 pi, that's a 0, right? It's all 0 there, so we can sum between 0 and pi. Right, so that's the sum of all the points there. Now, what's the number of points we're going to divide? So it's going to be, by the way, this is Vm, right? So Vm sine omega t. Sorry. So I'm going to take that Vm outside, and I'm supposed to now divide by 2 pi. When we integrate sine, what do we get?
Cos. Minus
Cos. Right, minus cos. So remember, power electronics involves mathematics as well. It's quite multidisciplinary. So minus cos omega t, right? So between 0 and pi. So our Vm for 2 pi. Right, so what do we get here? Cosine of pi is what? Hmm?
I think it's
What's
1.
One. One. Is it one?
1?
One.
So this would make it minus 1.
Minus.
It will be 1, sir.
Cosine
Mhm.
0.
It will be
Minus 1 minus the cosine of 0.
positive 1, sir.
Right, this should be, it's minus 1. Cosine of 180 is minus 1, right? So this should be positive 1, right? Is that
Yes.
right? So that's
Yes.
positive 1. And then you're going to
Minus.
minus that cosine
Of 0.
0. So this would make this plus 1, right?
Yes, sir.
So what we have here is Vm over 2. Right, so that's how we get our average output voltage. So it's
Sir,
average
is it over 2 or over 5?
over pi. That's an error right there. Over pi.
Where is the 2, sir?
Huh?
Get cancelled.
Oh, it cancelled.
Right.
1 plus 1. Yeah, the 1 plus 1.
Right. It's cancelled. All right.
Okay.
Right. So that's how we got this output to be Vm over 2 pi. All right. So when we look at our other device here, our silicon control rectifier, right? You can actually do the same thing. Let me just keep this. I'm going to just introduce something else. All right, so in the case of our silicon control rectifier, right, and of course we have our signal Vm sine omega t. All right, with that kind of device, right, you can actually start at different points depending on the pulse. right? So let us say we start here. VM. All right, so at this point we have our pi, and here 2 pi, right? And of course, at this point, it's the narrow pulse that we apply. So how do we calculate the average output voltage, right, for this waveform? Right, so that would be equal to the integral. Right, we're going to take the sum. Oh, by the way, I should mention that we refer to this point at which it starts. Let's say it's alpha. That's our delay angle, right? Delay angle alpha, right? So in this region, we refer to it as the delay angle. So let me just make note of that, right? So alpha is your delay angle. All right, so we take the sum sine omega t, and we're going to integrate with respect to omega t. And where we take this sum is between now alpha and pi, between alpha and pi. And what are we dividing by? What's the total signal here? Right? Our total is going to be 2 pi. So Vm over 2 pi. All right. And you can go through this one in a similar way. So the integral here, the Vm over 2 pi minus cosine right? So what's this equal to? All right, so it's clear that this is Vm over 2 pi, and you substitute, so that's minus cosine of 180. Again, we see that's just 1, and then we have the minus there, so this is going to be plus cosine alpha. So unlike with just the diode, we're getting only a fixed output, where we saw the average output was just the peak divided by pi. Here, we're seeing that we're able to vary our average output voltage by changing our delay angle, right? I should also mention that we also call this firing angle, right? Firing angle. right? So by changing the firing angle, we are able to change the average output voltage, right? So this is how we can use this concept to control the speed of like a DC motor, right? We just change the firing angle on the thyristor, and we are able to change the average output voltage. Of course, we'd have studied in the electrical machines and drives different ways that you can control the speed of a DC motor. You have the field control, you have the armature control, right? All these different methods, right? So by connecting this SCR across, it could be a field, it could be armature, you'll be able to vary the speed of your motor, right? So that's just one application. And if you think even more, you could connect this same circuit, let's say, across a lamp, right? By vary alpha, you'll vary the brightness of that lamp, right? So there are myriads of applications that this can actually be utilized in. And any questions, by the way? All right, no question. But yes,
On the other slide, you were writing.
go back to the previous slide.
Yes, sir.
This one.
Oh no, not that one. The where we were discussing the firing angle and such.
This one.
Yes, sir.
Right. Yes.
Yeah, just writing after for a second.
Okay. All right. All the slides that I have here, all the material that I cover to be made available to you via the Canvas platform. I think earlier on the slide that I wrote on, I think I didn't save it, so but it would be in the recording. I'll make sure that this one, these things that I've written, it will be saved on the slide for you. All right.
Okay, sir. You can move.
All right. So basically, I've mentioned these already. So our focus in this section of the course is going to be on the converters, and in particular the devices that we will use in the converter. As I've mentioned before, with power electronics is associated with the green technology. There's the need to reduce dependence on fossil fuel, and by fossil fuel I mean like natural gas, your coal, and so on. We expect this to deplete at some point, so we have to start utilizing our renewable energy sources like our wind, your solar, and so on. So you will find power electronics in these areas: solar, wind, a fuel cell. You'll find power electronics there. Right. So with power electronics, right, you can actually realize a 30% savings when you use the variable speed compressor, right? Earlier on, I showed that to you, right? As an example of one of the static, the drive mechanism that we have in power electronics. So 30% savings can be realized when we actually compare this to thermostat control system, right? So the older type of units, that's the one that you'll not see the inverter type written on it, right? What is inside is the thermostat. Also, I mentioned the static application, right? So the static application inside the electronic ballast, you'll find power electronics in there. Next time you open one, what you're looking at, those circuits in there, it's power electronics, right? You can realize up to 20% savings there, right? So when we look at environmental issues, right? The nuclear is quite safe, right? However, the radioactivity can be a problem, right? That can be a problem when we produce energy from fossil fuel. We have our greenhouse gases that cause global warming and acid rain and so on, all these effects, right? So a solution is the use of power electronics, right? It can tap into those renewable energy sources, right? You have electric vehicles now, right? In there is a lot of power electronics, right? So power electronics is growing rapidly, right? As we have semiconductor technology being advanced. You can also find it in a number of areas. Like I've mentioned, it's quite interdisciplinary in nature when you actually study it. So the switches, as I've mentioned earlier on, could be any of those power semiconductor switches. But for simplicity, I normally just do the illustration using a simple on-off switch. So what I'm showing you here is something that I've discussed in the introduction, the idea of switching loss. Right, so with the ideal switches, we will have no losses, but in reality, we're going to have losses, and the losses are normally when we have our transition between on and off, right? Because it's not an instantaneous process going from on to off or off to on. All right, so the important point to note that these switches, they're not linear. And I now move to the part where I will now classify these devices. The first one, we say, is uncontrolled. When we say uncontrolled, it's always going to be the diode that we're talking about, right? Semi-controlled, it's the thyristor that we're talking about, right? And the fully controlled, it could be any of the other devices like the IGBT, the MOSFET, the BJT, GTO, and the IGCT, right? So just keep in mind this classification. Uncontrolled is a diode, right? Semi-controlled is thyristors that we're talking about. Here, I will show you a picture of what our uncontrolled device looks like, or power diode, right? You'll see it here. That's the first one. This is one type, right? So the hockey puck type, and we have the IGBT. We've studied this device in more detail. This is one type for the full bridge and the three-phase, right? This type. We also show you here a picture of your IGCT. All right, so normally I must say this part, students normally find it a bit boring, but you must understand the devices, right? Must understand them before you can apply them to your design. So I will quickly run through them. The first one is the uncontrolled type. That's a power diode, right? So I have a symbol here. We have a A denoting the anode and a K for the cathode. If we look at the IV, typical IV characteristics, we can see here that it starts conducting after it reaches a particular threshold voltage, typically 0.2 to about 3 volts. Then it goes into the conduction state, right? In the reverse state, and this, we'll look at this side, it's quite a small leakage current that we observe at this point. It's normally the order of microampere to milliampere that will flow in that reverse blocking state, right? So important to note, we don't normally operate our diode in the reverse voltage state, whereby we have it greater than that voltage, that reverse voltage, right? If we do so, then we're actually breaking down the structure of your device, right? So we don't normally operate beyond this reverse voltage threshold. The reverse recovery, if we look at this switch, this graph of what is happening across our switch, as you can see here, we start with our high current, and then it's going to go down and go towards 0. So we're going from our on state to our off state, right? So the top curve that represents current, and the bottom curve, that's your voltage here, right? So when the current is high, we have the voltage being low. So in the on state, current flows, however, the voltage across your switch is 0, right? So as you switch from off to on, you can notice that the voltage increases, right? So that's your VR here. Now, how do we define our reverse recovery in this case, right? It's just the difference between this time that it takes to go towards 0. The current switches from the off state where it's high, and then it settles at this point. And then the T0, that's basically where it starts out at that high point. So this process of going, of turning on and off, as I've said, it's not instantaneous. You will perhaps be able to appreciate at this point why it can't be instantaneous. It will require some amount of time for those majority carriers to actually settle, right? To recombine, right? The process, it takes some amount of time. So what we'll end up having is some amount of losses in these devices. And we have a softness factor. If you look at these curves, what is happening. So to note from this, if we have a softness factor, as we increase the softness factor, look at what is happening. We have our device having less transient, right? It goes towards steady state in a more smooth way, right? So it's just a ratio that is used here, where in this case the difference between the T2 here, right, where it settles and where it starts from, between the current and the voltage times. So as we increase it, we observe that it is more smoother, right? Our transient is minimized. The line frequency diode, right? This type is a general purpose type diode. It has a large reverse recovery time, typically about 25 microseconds. And this is considered to be a slow response time. However, if we look at the current rating, it can go as high as 5 kiloampere, and it has a very high voltage rating, as high as 5 kilovolts, right? So this can be used in applications that require rectifications, right? We also have the fast frequency type. This one, the reverse recovery time is very low as 1 microsecond, right? So we have a faster response in this case. And when we look at the power levels, right, from several hundred volts, it can go up to as high as several hundred amperes. We also have what we call a Schottky type diode, right? So this type is used mainly in low voltage, high current type application, right? It has a small voltage, typically 50 to 100 volts, and of course the threshold voltage is about 0.3 volts that is required for it to, once overcome, will go into the conduction state. Now the thyristor, and more so the silicon control rectifier, right? This type of device, it has 3 terminals, right? Mainly anode, cathode, designated normally with the letter K. We also have G, right? The gate. All right, so this type, as you can see, it looks, it's almost like a diode if you look at it. If we just remove the gate, right? It's basically a diode. The key difference here, with the introduction of the gate, we're able to control the average output voltage of this device, right? Remember when I showed you earlier on the diode, the average output voltage was fixed, right? So researchers during that time, they're thinking, can we change the average output voltage? And that is when the thyristor came on the scene. That when, by introducing that gate to to this diode, right? By doing so, we're now able to control that average output voltage. So if you look at the curve, it is looking very much similar to the diode. The only difference is with this type of device, we can turn it on at different points. Now, we have our breakover voltage, right? So once it's exceeded, the device goes into conduction state. Yes.
So what is the difference between the thyristor and a transistor? Because it's kind of similar to me.
All right. We will soon get to that device in a little while. Yes. There, as you can see, as we progress, you will see the subtle differences. So before, we have this device uncontrollable. We can't change the output voltage. Now we have a device that we're able to control the output voltage, right? So the transistor, you will see that we're able to have some amount of control as well, right? But I will look at it in about the next 3 or so slides. All right, so let us just finish this part. So once we overcome this breakover voltage, then we are able to drive this device into its conduction state. Very important to note here is that once this device is turned on, right, using that positive pulse at the gate, after it's on and you remove that pulse, it will remain in the conduction state, right? So at this point, we say the device is latched, right? Very important. How can we turn this device off? There are techniques we refer to as commutation techniques that we can use to bring this device to the off state. There are two methods, either forced commutation or natural commutation. Right, so with the forced commutation, as long as we are able to just introduce some kind of circuitry, we reduce the current flow between the anode and the cathode, right? Then we'll be able to turn this device off, right? So natural commutation is as if when we connect, for example, let's say an AC, you know, it moves between the positive cycle, negative cycle, right? So when inside the positive cycle, if it is on, as soon as it goes to the negative cycle, then it's going to naturally drop the current flow between the anode and the cathode, forcing the device to go into the off state. Right, so it's pretty much like a diode, and we have them in different flavors, different sizes, right? It ranges from typically 1 amp up to as high as 1,000 amperes. All right, so I think I mentioned this part already. I'll talk about the method of commutation, natural commutation, and the forced commutation, right? So that's when we actually implement some kind of circuitry that will allow us to cause the current to move into another area, basically diverting it to another section, thereby reducing the current that is flowing between the anode and the cathode. We have, as I've shown you a short while ago, different types. We have phase control, inverter grade, light activated. We also have the triac type of thyristor. Right, so with phase control type, it has a low on-state voltage drop, right? So that's typically of the order of about 1.5 to 3 volts. However, it has a quite a large voltage that it can actually use as high as 7 kilovolts, and current can go as high as 4 kiloampere, right? So where you'll find applications of this basically for AC and DC motor drives, that's where you actually find this type of thyristor. There's an inverter grid type, right? So this type you find it in your inverters, your choppers, right? And it's quite a fast, right? And you can basically control it by way of force commutation method. There's the light activated type. I'll go into some more details with that one later on. So basically it uses a light. It shines onto the base, the gate, right? The gate of this thyristor is then activated. So normally this type is used when we want to have some kind of circuit isolation, the high powered side of the circuit and the high and the low powers. You want to isolate them as much as possible. Then the light activated type of thyristor is normally used. There's also the triac. This one has dual polarity. The SCR that we look at, you saw where it removed the negative portion of the cycles. However, with the triac, you can still control the output in the negative cycles as well as in the positive cycles, right? So this is another development, right? So after the SCR was designed, the thought was, how can we make use of those negative cycles? So the triac came on the market. Now, you mentioned the transistor, right? So the power transistor, right? So these types, basically, it works pretty much like the transistors, those small signal transistors that you studied when you did devices, right? Very much similar in operation, right? They're basically on-off switches, right? You normally apply some small voltage at the base, let us say the BJT, small voltage at the base, and then you're able to control, let's say, much larger voltage, right? So when the base voltage is applied, transistor is on, it can control a much larger voltage, right? So you say it goes into saturation and cutoff modes, right? So saturation turns fully on, and cut off, that's when it's off, right? So we don't have any latch mode as in the case of the SCR, right? So the SCR, after it is driven into conduction and you remove the gate control, it will remain in its on state. With transistor, after you have applied your gate voltage that was sufficient to switch your transistor on into the saturation state, moving if you remove that base voltage, your transistor will go off, right? So there's no latching feature. So that's the difference. These are some newer devices that we'll be looking at. The MOSFET, that is metal oxide silicon field effect transistor. We'll be looking at the IGBT, that's insulated gate bipolar transistor. GTO, right, that's the gate turn off thyristor. And newer type, the gate control thyristors. We'll be exploring those. If you recall, earlier I mentioned that I will bring those newer type devices early in the course as opposed to later down in the course. All right, so the BJT, you should be familiar with it. You have your base, your collector, your emitter, and of course the typical IV curve is shown here in the top right hand corner. All right, now this type has will have voltage rating as high as 1000 volts, current as high as 400 amperes, and your switching frequency, right? This is a very important point to note. The switching frequency of these devices, right? 5 kilohertz, right? So when it's time to design your power electronic circuit and you're selecting a particular switch, right? The switching frequency, the power rating, right? Current, the voltage, these are important specifications that you'll have to pay attention to in selecting a particular device in your application, right? So you should have some knowledge. All right, so here, this type, it has a low current gain, typically about it's less than 10, right? So based on that, you will need a high base current to obtain a reasonable amount of collector current. And very important to note with this device, right? It can be expensive and complex base drive circuits are normally required. So now this device is not so popular in power electronics, right? So if there's a time where we need to increase the drive current, then you can use this combination. We refer to it as a Darlington pair, where we turn these transistors back to back in this fashion. All right, so how do we realize that higher gain as compared to just using this, looking at this transistor by itself? All right, we can look at the math. All right, so by gain, it's the ratio of our collector current to the base current, right? So the ratio of collector current to base current. So we start off with our definition, beta. So from IC to IB1. So that's your ratio. However, if we look at what constitutes the collector current, you'll see here it is going to be IC1 as well as IC2, right? look right here. IC, it splits to IC1 and IC2. So in the proof, I can just expand this idea here. So IC is equal to the summation of IC1 and IC2. All I'm doing next is to just break this up. So this is just IC1, that's the collector current on the first transistor, to beta 1, and then we have the collector current on the second transistor to the ratio to the current on the first transistor IB1. It's just fractions here. We're just splitting this, expanding the brackets right here. That's all we're doing at this point. Now, right here, IC1 to IB1, that one is clearly the gain on transistor 1. So we can call that beta 1. Right, so call that one beta 1. And now, what are we going to do here? So a little trick step right here, just to simplify the proof. Okay, so if you look at this, IC2 to IB1, right? So I'm going to multiply the top and bottom of this by IB2, right? So that's all I'm doing right here. Multiplying the top, that part, right, top and bottom by IB2, right? So we're not really changing this ratio. All right, so by doing that, we now look at IB2. What is IB2? Right, if you look, it's going to be the sum of IB1 and IC1, right? Just look at the IB2, right? This is IB2, right? So what do we have here? We have IB1 and IC1, right? So that's the combination that makes up your IB2 here. So what can we do here? We're now going to split this up. So, I beg your pardon. Right, so we now split this part up and then expand it. Right, so we factor out our IB2 right here. Right, so if you look here, the ratio IB1 to IB1 to IB1, this one is basically 1, and IC1 to IB1, that's basically beta 1. So when we expand this, what we observe, overall beta is larger, so we have a higher gain. Any questions? All right, now we can move on to the MOSFET. Right, so for our MOSFET, we have these three terminals. We have our drain, our source, and our gate. The behavior is pretty much is somewhat similar to the BJT. All right, so this one it it has a turn on and turn off that requires a gate source voltage of typically 15 volts, right? So between 0 and 15 volts, you can use to switch it on and off. And the drain source voltage is as high as 500 volts, and your current is as high as 300 amperes. However, if you look at the frequency for this device, it's much larger than 1000 kilohertz. So if you are going for a high frequency, then a MOSFET is a preferred device. Very important to note, right? So high frequency applications, you will use your MOSFET. However, the power is very low, right? It can go as low as just a few 100 watts, and it goes up to megawatts. So for low power, high frequency applications, your MOSFET is a preferred device. And also the gate drive circuitry is very simple as compared to the BJT, where the drive circuitry is normally expensive and is complex. So in most power electronic applications that require high frequency, low power, the MOSFET is a choice, right? The power MOSFET. All right. I should mention also with this device, there's what we call it has some amount of resistance between the drain and the source. That's we normally use the RDS, right, to represent this resistance between the drain and the source. So as you know, with resistance, this is going to impact the overall efficiency of the device. So it's going to introduce here some amount of loss, right? So basically for high frequency, low power applications, the choice is a MOSFET. Now, another device came on the scene, right? It's referred to as the IGBT. What was the thinking at this point when this device came on the scene? There's a need for a device that could take basically the best of both worlds, right? From the MOSFET and from the BJT. What characteristics specially, right? So from the MOSFET, it was easy to turn on and off. So we want to get that characteristic, right? So from the BJT, as you can recall, it has the smaller losses, right? So where the MOSFET, you have that resistance between the drain and the source. With the BJT, you didn't have that kind of resistance that would impact significantly on the power loss in the device. So hence with the BJT, it had a lower power loss, right? And so these two features are actually used in the BJT. So this is basically a combination of these two devices, right? The IGBT, that's the insulated gate bipolar transistor. right? So it's taking the best of the two, right? Of course, it has voltage rating, can go as high as 3.3 kilovolts. Your current can go as high as 1.2 kiloamperes. And of course, if you look at your switching frequency, it's as high as 100 kilohertz. All right, so with this device, how can we actually control, right? We want to be able to control this device from the gate. How do we do that? So another device came on the scene. It's called a gate turn off thyristor. If you look at it, the characteristics is pretty much similar to that of a thyristor. Now, with your gate turn off thyristor, what is normally made use of here is the fact that you can turn it off by just using a gate signal. Unlike with the thyristor, when you remove the gate, the device was latched. The device remained on, right? So the thinking was, how can we get a device where we're able to control it from the gate, right? So the gate GTO came on the scene in response to that, right? So the SCR, that's a silicon control rectifier, as you can recall, when we remove that gate signal, it remained on, it was latched, right? Similar with the triac, we remove the gate, it remained on, it's latched, right? So with this device, we are able to control it from the gate, right? So it's very much similar in operation. The main difference is controllability at the gate. And the key things to look at here is the voltage. Anode cathode voltage can be as high as 5 kilovolts, or current can be as high as 5 kiloampere, and a frequency as high as 5 kilohertz. All right, so this device, it has quite a lot of competition, say from the lower end IGBT and the high end IGCT. All right, so another device came on, right? The insulated gate commutated thyristor. Again, with this one is in response to the thyristors, where you're not able to control the signal from the gate. Once you remove the gate signal, the device would remain on in its latch state, right? So with this one, you use the gate signal here to actually turn it on and off. But you're probably wondering, so what's the difference between the GTO, right? With the GTO, there's a problem. It is difficult to turn off, right? It is normally you require about 1/5 of the anode current. So they try to fix that problem, right? So with this device, you can turn it on and off with just 20 volts, right? So that's the key difference between the GTO and the IGCT. And of course, with this device too, these switches, you have integrated the drive circuit in them, right? So with the GTO, as I recall, it was the gate drive, the design was very difficult, right? Very difficult, and this was primarily because of the large reverse gate current that was required to turn it off. Now, if we look at the ratings, right? So that the anode cathode voltage can be as high as 6.5 kilovolts, and your current rating can be as high as 4 kiloamperes. Your frequency as high as 1 kilohertz. So it's fairly low frequency, high power, right? So any application that required this kind of low frequency with high power, you can select the IGCT. So those are the main devices that we will be working with. I have summarized the characteristics of the power with the frequency, as this will be very important for you when you're selecting a particular device for an application, right? So just summarize them here, so it will help you as you study these devices. The gate driver circuit. I will. All right, so there are two functions mainly our gate driver circuit will serve. One, amplification, and second one, isolation. All right, so as I can see here, our drive circuit, we would normally find it sitting between your control circuit and some high power application, or some switch, right? So it's sandwiched by a control circuit and their switch, and it can, in one instance, if it's functioning as amplifier, then it amplifies that signal that is required for your drive switch, right? So maybe you have some device in the field, and for some whatever reason, the signal that will be required, if you were to connect it directly to your switch, it may be too low to switch it on. So you need a drive circuit that will be able to amplify that signal so that it can be sufficient to operate your power switch. There might be instances where you need to have some amount of isolation, right? And by isolation, I'm talking about the electrical isolation. This could perhaps, this control circuit could be a signal from your microcontroller. It might be some logic level, right? Let's say 5 volts for high. You want to have some amount of isolation between your logic level and your power switch. All right, so when we look at the complexity of drivers, they can vary. As you have seen by what has been shown so far, the MOSFET and the IGBT, these are circuits that these devices will require simple drivers, as opposed to the GTO and the BJT, where they can become quite complicated and expensive. All right, so if we look at this circuit that we have here, this is one example that I'll use to demonstrate the whole amplification, right? So for amplification, so this is from our amplifier right here. Let's say our amplifier at the output of our amplifier here, we have a transistor Q, as you can see here. Let's say it's the LM311, and between here we have a very simple drive circuit network. That's 2 resistors, and we have our power MOSFET at this. So it's a very simple drive circuit that we have implemented between our control circuit and our power switch. Just 2 resistors we have here. So how is this? How this works? We have our voltage here. Let's say our source voltage at this point. When this transistor turns on, what is going to happen? What is going to be the voltage at this point? At this point, the voltage across, this is a switch, right? The voltage across this switch would be 0 when it is on. So hence we don't have any voltage drop across the gate source of our transistor. Hence this would be in the off state, right? So this would be off, right? However, at the output of our amplifier, let us say when it is off, right, we would have a voltage drop across the output, and thereby resulting in a voltage across the drain source, and that could be sufficient to switch this power MOSFET on, right? So now, very simple drive circuit here. If you look at isolation, we can use what we call a pulse transformer for isolation. If you look in here, this block, we could have just an LED. From our control circuit, we connect it to our LED. If it turns on, it shines light onto the base of a transistor, thereby switching it on, right? So no light, it switches it off. So therefore you can control power of a much larger circuit here. Higher power, so using a low power to control a high power circuit here. So we have electrical isolation, right, using optocouplers, right? We refer to this as optocoupler, right? So this table basically summarizes all of what I've been discussing so far as it relates to switches. Before, let me move to this one. Applications, right? So hopefully you have been paying attention, because at this point you will answer these questions. Hello? Hello?
Yes, sir. We're here.
Yes, yes.
All right. So the question is, you're going to be looking at these questions, and you see how it's applied. Your knowledge of those devices can be applied to different scenarios. All right, so I'm going to ask you to look at this, and for each of these applications, you're going to choose the best power switches and the reason. Um, I'm not sure if maybe I should let you look at this over the weekend. You review these notes, but I just want to let you have an idea as to why we went through that. You may have a scenario where you have an inverter for the light rail train, right? So LRT, locomotive operating from a DC supply of 750 volts. The locomotive is rated at 150 kilowatt, right? So the induction motor is to run from standstill up to 200 hertz with power switches frequencies up to 10 kilohertz. Right, so that's the situation. So you have your light rail train using induction motors, right? But you want to control this operation using your semiconductor switch. And these are the specifications, right? So 750 volts. So if you need to understand your current, it'll be based on the power rating. Also, you're told that you want a frequency between 200 hertz and 10 kilohertz, right? So which switch? So that's something that you will consider. Also, if we look at another scenario here, a switch mode power supply, or SMPS, for remote telecommunication equipment is to be developed. The input voltage is obtained from a photovoltaic array that produces a maximum output voltage of 100 volts and a minimum current of 200 amperes. The switching frequency should be higher than 100 kilohertz. Right, so that's another scenario there where you're going to have to analyze and select your switch. So the next one here, you have a high voltage DC transmission system transmitting power of 300 megawatts from one AC system to another system, right? And both are operating at 50 hertz, right? However, the DC link voltage is operating at 2 kilovolts, right? So you're going from as low as 2 kilovolts to as high as 300 megawatts in terms of power, right? So high voltage as high as 2 kilovolts and power as high as 300 megawatts and frequency just 50 hertz. All right, so are you able to provide me with answers for the three scenarios?
So I think number 3, the thyristor can work because it's a low frequency, high power application.
Yes,
Yeah.
yes. You can use thyristors there. That's correct. All right. How about the second scenario? If you notice, we have high frequency, but this is what should be a fairly low power, right? Low power. When we look at the voltage and the current, it's a fairly low power. So what device would you use here?
So MOSFET.
Right. Once you have low power, high frequency, you'll always select your power MOSFET. All right. The first scenario.
Not so sure about
All right. So what would you be looking at here in terms of frequency? Our frequency of about between 200 hertz and up to about 10 kilohertz here, and you have a power of just 150 watts.
sir. I think the power MOSFET.
Which one?
The power MOSFET.
Yes, you could use a power MOSFET here, right? Power MOSFET, right? To be able to handle that situation. All right. I think I'm going to maybe I should get a reach. All right. Let me just continue a little bit, maybe two more slides or so before we stop. I think it's best we break for today. We'll continue next week. Let me just keep this. So we'll continue this lesson next week. So we basically stop where we reviewed the application. So in today's class, we look at the different power semiconductor devices that are available. We look at key specification as it relates to their power, their voltage, and current and frequency. So based on these specifications, you're able to select the appropriate power semiconductor device for a given scenario. So that's basically pretty much what we look at, and we saw that when we're going for low power, high frequency applications, we always use our power MOSFET, right? For high power, low frequency, then we can consider devices like your thyristors or your IGBTs, right? So those are the kind of switching devices that you would consider. All right. Let me. All right, I should stop that.